The pre-Columbian indigenous peoples of the Americas utilized latex from Hevea brasiliensis trees to produce waterproof garments and heavy-duty containers. The extraction process involved incising tree trunks, collecting the exuded sap, and employing natural coagulation methods. This technique demonstrates an early understanding of polymer chemistry and material science. The economic impact included localized trade networks centered around rubber production. Material, latex. Process, incision and coagulation. Economic outcome, regional commerce expansion. The extraction of natural latex in pre-Columbian societies was a meticulously engineered process that reflected both an intimate understanding of botanical physiology and a sophisticated approach to material science. Hevea brasiliensis trees, native to the tropical regions of South America, were the primary source of this viscous sap. Indigenous producers employed a technique that balanced efficiency with sustainability. Shallow incisions were made across the bark using sharp stone tools or flint blades, angled at approximately 30 degrees to maximize exudation without compromising the tree's structural integrity. These wounds were strategically spaced along the trunk and branches, ensuring that no single area was overexploited during a harvesting cycle. The latex, a milky white fluid rich in polyisoprene polymers, flowed slowly from the cuts into hollowed gourds or carved wooden vessels positioned beneath the wounds. These collection containers, often crafted from durable materials such as hardwoods or hardened plant fibers, were designed to minimize contamination and evaporation. The process was typically conducted during periods of low humidity, a critical factor in maintaining the latex's viscosity and preventing premature coagulation. Over time, these techniques allowed communities to harvest large quantities of raw material without depleting their resource base, underscoring an advanced ecological awareness that predated modern conservation principles. The economic implications of this method were profound. The ability to produce consistent yields of high-quality latex enabled the development of trade networks that extended across vast distances, linking coastal regions with inland settlements through complex systems of exchange. This extraction process was not merely a technical achievement, but a cornerstone of sociological organization, requiring coordinated labor, specialized knowledge, and hierarchical management of resources, mechanisms that would later influence broader economic structures in the region. As this segment concludes, the intricate interplay between botanical science, material engineering, and social coordination becomes evident, setting the stage for an exploration of how these raw materials were transformed into functional objects with an enduring utility. This is Elias Untold Vance. Let us now delve deeper into the technological innovations that turned latex into waterproof garments and heavy-duty containers, revealing the hidden mechanisms that shaped pre-Columbian economy. The chemical composition of natural latex, primarily polyisoprene, dictated the methods by which pre-Columbian societies manipulated its physical state. Polyisoprene molecules, arranged in long polymer chains, exhibited inherent hydrophobic properties, resisting water absorption while maintaining elasticity when in liquid form. However, this fluidity posed challenges for practical application. To transform latex into a solid, durable material, indigenous producers employed coagulation techniques rooted in environmental and chemical interactions. Exposure to air-initiated oxidation processes, causing the latex to thicken and solidify over time. This method relied on controlled evaporation of volatile components, leaving behind a fibrous matrix that retained tensile strength. Alternatively, heat application, often achieved through direct contact with heated stones or fire-heated vessels, accelerated molecular cross-linking, producing a more rigid yet still pliable substance. The most sophisticated approach involved the use of natural coagulants derived from plant ash, which contained alkaline compounds capable of neutralizing acidic components in latex. This reaction triggered rapid precipitation of polyisoprene molecules into a cohesive mass, enabling precise shaping and molding. These techniques were not merely empirical, but reflected an understanding of material science principles, as the resulting rubber exhibited hydrophobicity, flexibility, and resistance to degradation from moisture or mild abrasion. The economic implications of such mastery were profound. The ability to produce waterproof garments and containers expanded trade networks, allowing societies to transport perishable goods across arid regions or store surplus agricultural products. During seasonal scarcity, rubber's utility extended beyond practical applications. Its production became a specialized craft, often monopolized by elite classes or specific social groups, reinforcing hierarchical structures within communities. By controlling the coagulation process, these societies ensured that rubber retained its functional properties while maintaining economic leverage through scarcity and exclusivity. The technical sophistication of these methods underscores a deliberate integration of natural chemistry into daily life, revealing an ancient technological paradigm where material manipulation was as much a social mechanism as it was a scientific achievement. Don't forget to subscribe to the channel, follow us, and turn on the notification bell to stay updated with our upcoming historical journey. The transformation of raw latex into functional waterproof garments involved a sequence of meticulously controlled processes that demonstrated an advanced understanding of materials science by pre-Columbian artisans. Once collected, latex was coagulated through exposure to acidic substances derived from crushed tree bark or charcoal ash, which accelerated its transition from liquid to solid form without compromising elasticity. This coagulated rubber was then kneaded manually for hours, a labor-intensive step that aligned the molecular structure of the polymer chains, enhancing both tensile strength and flexibility. The prepared material was subsequently pressed into wooden molds carved with intricate geometric patterns, often featuring interlocking segments designed to replicate the seamless curvature of human limbs. These molds were heated using volcanic stones or open fire pits, applying uniform pressure that forced the rubber into every recess of the design while maintaining its hydrophobic properties. Once cooled, the sheets were removed and cut into precise panels using stone-bladed tools, their edges trimmed to ensure a tight fit when assembled. The final stage involved stitching these pieces together with fibers extracted from agave or cotton, which had been pre-treated with natural resins to reinforce their tensile strength. The resulting garments exhibited remarkable resistance to water penetration, achieved not only through the inherent properties of rubber, but also via the strategic layering of multiple sheets in critical areas such as seams and joints. This technological innovation held profound economic implications, as the production of waterproof clothing became a specialized craft that required access to specific raw materials, latex producing trees, hardwood for molds, and fibrous plants, which necessitated well-established trade networks spanning hundreds of kilometers. The demand for these garments among elite classes and labor-intensive communities further entrenched rubber production as a cornerstone of regional economies, while the secrecy surrounding the precise formulations of coagulants and resins suggests an intentional effort to preserve technological advantage within certain social groups. The integration of rubber into daily life thus reveals a complex interplay between material innovation, environmental adaptation, and socio-economic stratification, underscoring the depth of pre-Columbian engineering capabilities long before the advent of industrial chemistry. The production of heavy-duty containers from natural latex in pre-Columbian societies involved a precise interplay of thermal manipulation, mechanical compression, and chemical stabilization. Indigenous artisans employed controlled heating methods, often using open fire pits or heated stones, to soften raw latex, rendering it pliable enough to be shaped into forms. This process was not merely about malleability. The application of heat also initiated subtle polymerization reactions within the latex, enhancing its tensile strength and elasticity. Once softened, the material was pressed into molds crafted from stone, clay, or carved wood, which dictated the container's final shape. These molds were often designed with intricate patterns, suggesting both functional and ceremonial purposes. To achieve durability, producers incorporated natural coagulants derived from local flora. Resins extracted from species such as Proteum, a genus of tree native to Central America, or alkaline-rich plant ashes acted as cross-linking agents, accelerating the vulcanization process without modern chemical additives. This method not only increased the rubber's resistance to deformation, but also imparted a degree of waterproofing critical for storing liquids like chicha, fermented maize drink, or medicinal extracts. The resulting containers exhibited remarkable resilience. Archaeological findings from sites in present-day Peru and Brazil reveal intact vessels capable of withstanding prolonged exposure to moisture, temperature fluctuations, and physical stress. The economic implications of such production were profound. These containers facilitated the storage and transport of surplus agricultural goods, enabling long-distance trade networks that connected lowland river systems with high-altitude settlements. In regions like the Amazon basin, rubber's role extended beyond utility. It became a commodity in early exchange systems, traded for obsidian, shell ornaments, or coca leaves. The ability to create waterproof storage solutions also influenced dietary practices and food preservation techniques, allowing communities to stockpile grains during harvest seasons and mitigate risks from environmental variability. From a sociological standpoint, the labor-intensive nature of rubber production reinforced specialized craftsmanship within communities. Artisans who mastered the technique held elevated status, their knowledge passed down through generations as part of oral traditions or apprenticeship systems. The containers themselves often bore symbolic carvings or pigments, indicating ownership by elite classes or use in ritual contexts. This duality, practical innovation intertwined with cultural significance, underscores how technological advancements in material science were deeply embedded in the social fabric of pre-Columbian societies. By leveraging environmental resources with minimal ecological disruption, these techniques exemplify an early form of sustainable engineering. The absence of synthetic additives and reliance on renewable materials reflect a holistic understanding of material properties that modern industrial processes only began to replicate centuries later. This segment concludes by emphasizing how the production of heavy-duty containers was not merely a technical achievement, but a cornerstone of economic resilience, social stratification, and ancient America adaptation in ancient America. The production of rubber-based goods catalyzed a transformation in pre-Columbian trade dynamics, establishing a network of exchange that transcended localized communities. Archaeological evidence from the Amazon basin reveals that latex-derived items, such as waterproof containers and elastic cords, were transported over hundreds of kilometers, often alongside obsidian blades, shell beads, and coca leaves. These exchanges were not random. They followed structured pathways dictated by environmental corridors and existing kinship alliances. Rubber's utility as a durable material for storage and transportation enabled societies to surplus-produce goods that could be traded for non-local resources, such as salt from coastal regions or copper ores from the Andean highlands. This interdependence fostered economic specialization, with some groups focusing on rubber extraction while others concentrated on metallurgy or agriculture. The demand for rubber also influenced labor organization, as communities required coordinated efforts to harvest latex from Hevea brasiliensis trees, a process involving meticulous tapping techniques and seasonal timing. In the Maya lowlands, rubber balls used in ritual games were traded as status symbols, linking economic value to socio-political hierarchies. Meanwhile, in Mesoamerica, rubber was embedded into trade agreements that regulated access to critical resources like maize and cacao, reinforcing alliances between city-states. The material's versatility ensured its role in both everyday utility and ceremonial contexts, creating a dual economy where practical needs intersected with symbolic exchange. This system of trade did not merely transfer goods. It redistributed knowledge, as techniques for rubber processing spread across regions through contact and competition. In the Andes, for instance, the use of rubber to seal ceramic vessels for long-distance transport mirrored similar practices in the Amazon, suggesting a diffusion of technological innovation driven by economic necessity. However, this interdependence also introduced vulnerabilities. When environmental shifts or resource depletion disrupted rubber production, entire trade networks faced collapse, as seen in the decline of certain Mississippian cultures during periods of prolonged drought. The economic impact of rubber thus extended beyond material exchange, shaping social structures, political power, and even ecological management strategies. By embedding itself into the fabric of pre-Columbian economies, rubber became a silent architect of connectivity, influencing the rise and fall of civilizations through its role in both sustenance and commerce. Don't forget to subscribe to the channel, follow us, and turn on the notification bell to stay updated with our upcoming historical journey. The material characteristics of pre-Columbian rubber were not merely incidental, but deliberately harnessed through empirical refinement over centuries. When processed correctly, natural latex exhibited an elasticity that could stretch up to 800% of its original length before returning to its form, a property achieved through precise control of vulcanization-like processes using heat and plant-based gas. Catalysts such as chicle from the acerola tree. This elasticity was critical in applications requiring resilience, such as the production of ball game equipment by the Maya and Aztecs, where rubber balls were subjected to repeated impacts without degradation. Simultaneously, the hydrophobic nature of cured rubber, reinforced by coating with resinous substances derived from Copaifera species, created a barrier against water penetration that rivaled modern synthetic materials. This property was exploited in the manufacture of waterproof garments and storage containers, essential for preserving foodstuffs in tropical climates where humidity accelerated spoilage. Archaeological analysis of rubber artifacts from the Olmec heartland reveals microstructural evidence of deliberate porosity reduction through compression techniques, enhancing durability while maintaining flexibility. A feat that modern polymer scientists have only recently begun to replicate with precision. The economic implications of these material properties were profound. Regions capable of producing high-quality rubber gained leverage in interregional trade networks, as evidenced by the presence of rubber artifacts in distant coastal settlements. Far from primary latex sources, this technological mastery allowed societies to develop specialized industries, such as the production of rubber-coated fishing nets that could withstand prolonged submersion without losing tensile strength, thereby increasing aquatic resource yields and reinforcing socio-political hierarchies centered around control of raw material distribution. The integration of rubber into daily life extended beyond utility. Its inherent resistance to microbial degradation made it an ideal medium for preserving ceremonial artifacts, as seen in the undecayed rubber figurines recovered from burial sites in England. The Amazon basin, where organic materials typically decompose rapidly under humid conditions. These applications underscore a level of material science sophistication that predated European contact by millennia, demonstrating that ancient American societies did not merely adapt to their environments, but actively shaped them through technological innovation rooted in an intimate understanding of natural material properties. The technological ingenuity of pre-Columbian rubber production reveals a striking parallel to contemporary polymer engineering. Modern industrial applications of synthetic polymers, such as neoprene, polyethylene, and silicone, are often celebrated for their adaptability in waterproofing, elasticity, and durability. However, The methods employed by ancient Mesoamerican and Andean societies to manipulate natural latex demonstrate an early mastery of material science that rivals these modern achievements. By examining the functional design principles embedded in their rubber-based artifacts, we uncover a sophisticated understanding of polymer behavior that predates industrial chemistry by millennia. Natural latex, derived from Hevea brasiliensis trees in the Amazon and other native species across the Americas, was processed through techniques that inherently optimized its molecular structure. Ancient artisans employed heat treatment, mechanical stretching, and chemical coagulation to alter the latex's properties, effectively creating materials with tensile strength comparable to modern vulcanized rubber. This process mirrored contemporary polymer cross-linking methods, where molecular bonds are reinforced to enhance resilience. For instance, the production of waterproof garments by the Maya and Aztec civilizations involved coating textiles with a thin layer of coagulated latex, a technique analogous to the application of polyurethane coatings in modern rainwear. The resulting material exhibited hydrophobic properties, preventing water penetration while maintaining flexibility, a feat achieved without the use of synthetic additives or industrial machinery. Economically, the production and trade of rubber-based goods in pre-Columbian societies functioned as a decentralized yet highly specialized system. Rubber was not merely a commodity, but a resource integral to economic networks spanning vast regions. The labor-intensive process of harvesting and processing latex required coordinated efforts among communities, reflecting an early form of industrial specialization. This mirrors modern polymer manufacturing, where raw material extraction, refinement, and application are segmented across global supply chains. However, unlike contemporary systems reliant on fossil fuels and petrochemicals, ancient rubber production was rooted in sustainable ecological practices, utilizing renewable resources and minimal environmental disruption. The functional design of pre-Columbian rubber artifacts further underscores their technical sophistication. Waterproof containers crafted by the Zapotec and Olmec peoples employed a combination of latex lining and woven plant fibers, creating vessels capable of storing liquids for extended periods without leakage. This innovation parallels modern composite materials used in industrial storage solutions, where polymers are integrated with reinforcing structures to achieve durability and impermeability. Similarly, rubber-soled footwear developed by indigenous groups in the Andes demonstrated an understanding of friction dynamics and wear resistance, principles later formalized in the development of synthetic rubber for tires and athletic gear. By analyzing these historical applications, we recognize that pre-Columbian societies did not merely exploit natural resources, but engineered materials with precision tailored to specific environmental and economic demands. Their ability to manipulate latex at a molecular level, long before the advent of industrial chemistry, highlights an advanced comprehension of polymer science that challenges conventional narratives of technological progress. This comparison underscores a critical insight. The principles of material innovation are not confined to modern laboratories, but are deeply embedded in the ingenuity of ancient civilizations. The legacy of these techniques persists today, subtly influencing contemporary practices in waterproofing, industrial manufacturing, and sustainable resource management, proving that the foundations of polymer science were laid long before the first synthetic compound was synthesized in a laboratory. The environmental sustainability of pre-Columbian rubber production hinged on a precise balance between resource extraction and ecological preservation. Hevea brasiliensis trees, the primary source of latex, were tapped using stone or shell-bladed tools that incised the bark without severing vascular tissues. This method allowed for repeated harvesting over decades, as the tree's natural regenerative capacity ensured continuous upflow. Unlike later industrial practices involving deforestation and chemical coagulants, indigenous techniques relied on plant-based catalysts, such as chonta palm juice or ash derived from hardwood fires, to accelerate latex solidification. These substances, rich in tannins and alkaloids, acted as natural cross-linking agents, enhancing the material's durability without degrading soil fertility. Archaeological evidence from sites like the ancient Maya city of Copan reveals that rubber production zones were strategically located near riverine ecosystems, where water tables supported rapid latex coagulation. Workers collected fallen rubber sheets or molded them into objects using heated stones, a process that required no synthetic additives. The biodegradability of these artifacts, discovered in burial contexts and trade routes, suggests that discarded rubber items decomposed harmlessly, minimizing long-term environmental contamination. Economically, this sustainability enabled extensive trade networks across Mesoamerica and the Andes. Rubber's waterproofing properties made it indispensable for crafting storage containers, boat caulking, and even ceremonial artifacts. The absence of resource depletion ensured that communities could maintain production cycles without overexploiting forested areas. In contrast to agricultural societies reliant on arable land, rubber-producing groups leveraged the resilience of tree species, creating a low-impact economic model that prioritized intergenerational resource access. Visual prompts: a close-up of a stone blade slicing into a Hevea brasiliensis trunk, a worker applying Shanta palm juice to a latex-coated cloth, a riverbank where rubber sheets are sun-dried, a cross-section of tree bark showing unbroken vascular tissue post-tapping, an Andean artisan molding rubber into a vessel using heated volcanic rock, a trade route map with rubber artifacts marked along Mesoamerican trade paths, a comparison of soil samples from tapped and untouched forest areas, i.e., ceremonial ball used in the Mesoamerican ball game, its surface textured from repeated latex application, a sequence showing biodegradation of rubber sheets buried in sediment layers, an illustration of a pre-Columbian toolkit, including stone blades in ash-coated containers, a diagram of tannin molecules interacting with latex proteins during coagulation, a worker using a reed to remove excess sap from a tree's incision site, a panoramic view of a rubber processing center near a river delta, and analysis of pollen data indicating stable forest coverage over centuries. A reconstructed scene of a community gathering to harvest latex during seasonal cycles. A microscopic image of latex particles adhering to plant-based coagulants. A comparison of modern chemical coagulation methods with pre-Columbian plant-derived alternatives. A sequence showing the reuse of rubber, scraps in crafting smaller tools. An archaeological site where rubber artifacts are found alongside agricultural implements. And a graph depicting consistent rubber yield rates across multiple decades of tapping. Don't forget to subscribe to the channel, follow us, and turn on the notification bell to stay updated with our upcoming historical journey. Rubber's role in pre-Columbian societies extended far beyond its practical applications, embedding itself deeply into the spiritual and social fabric of numerous indigenous cultures. Archaeological evidence from regions spanning Mesoamerica to the Amazon basin reveals that rubber was frequently incorporated into ceremonial objects, often serving as a medium for expressing cosmological beliefs or marking ritualistic transitions. Among the Olmec civilization, for instance, rubber was used to craft sacred balls employed in elite games, which were not merely athletic contests, but acts of divine communication, believed to mediate between human and celestial realms. These artifacts, often embedded with pigments derived from cacao or obsidian dust, underscored the material's association with power and spiritual authority. elevating its status beyond a utilitarian commodity. In the Andean highlands, rubber was similarly woven into the symbolic lexicon of pre-Inca societies. The use of latex-coated textiles in funerary contexts, particularly among the Paracas culture, suggests that rubber was imbued with protective or transformative properties, intended to facilitate the deceased's passage into the afterlife. Such textiles, discovered in tombs alongside offerings of llama bones and finely woven cloth, highlight a belief system where material substances were thought to bridge physical and metaphysical domains. The labor-intensive process of vulcanizing natural latex, achieved through heat and mineral catalysts, further reinforced rubber's perceived sacredness. Its durability and resilience mirrored the endurance of spiritual ideals within these communities. Economically, the cultural prestige of rubber influenced trade networks and social hierarchies. In the Maya lowlands, rubber was often exchanged as a form of tribute between city-states, with elite classes commissioning elaborately carved rubber seals to signify political alliances or religious decrees. These seals, sometimes embedded with jade or gold inlays, were not only functional but also served as visual assertions of power, their production requiring specialized knowledge that was closely guarded by artisan guilds. The economic value of rubber thus became intertwined with its symbolic weight, creating a feedback loop where demand for the material drove technological innovation while simultaneously reinforcing societal stratification. The integration of rubber into daily life further illustrates its multifaceted role. Among the Amazonian tribes such as the Sayona and Hutoto, latex was used to create waterproof containers that stored medicinal plants or fermented beverages, objects that were both practical and ceremonial. These vessels, often adorned with geometric patterns representing ancestral lineage, functioned as portable repositories of cultural memory. Similarly, rubber was incorporated into body adornments, such as bracelets and headdresses, that denoted social status or spiritual affiliation. The process of crafting these items, which required precise knowledge of latex coagulation techniques, was typically reserved for elders or shamans, ensuring that the material's symbolic potency remained within specific cultural custodians. The economic implications of rubber's symbolic use were profound. In regions where rubber production was centralized, such as among the Aztec Empire, the material became a critical component of tribute systems, reinforcing political dominance while also fostering regional interdependence. The demand for high-quality latex drove innovations in harvesting methods, including the development of specialized tools to extract sap without damaging trees, a practice that demonstrated an early understanding of sustainable resource management. These techniques, combined with the material's cultural cachet, positioned rubber as a linchpin in both economic and sociological frameworks, ensuring its enduring legacy long after the collapse of pre-Columbian empires. Pre-Columbian societies in Mesoamerica and South America faced significant technological constraints in manipulating natural rubber without access to synthetic chemicals or advanced metallurgy. Yet, their ingenuity manifested in controlled coagulation methods achieved through precise temperature regulation during latex extraction. By heating harvested latex to specific thresholds, often between 40 degrees C and 60 degrees C, these societies induced partial polymerization, stabilizing the material's viscosity for shaping. This process was documented in residues found on ceramic vessels from the Maya lowlands, which showed traces of heated latex mixed with ash derived from Erythroxylum species, a plant known for its alkaloid content that acted as a natural catalyst. Such methods allowed artisans to craft waterproof garments and containers without relying on modern vulcanization techniques. The use of organic compounds further exemplifies their technological adaptability. Archaeological evidence from the Andean region reveals that rubber was often blended with Hymenaea corboril resin, a substance extracted from leguminous trees native to the Amazon basin. This additive enhanced tensile strength and resistance to degradation, as evidenced by the durability of rubber-coated textiles discovered in burial sites dating to 500 BCE. Similarly, the Aztec Empire employed Amorphophallus titanum starch, a compound derived from a tropical plant, to modify rubber's elasticity for applications such as ball game equipment. These modifications were not arbitrary. They aligned with economic strategies that prioritized resource efficiency, ensuring that limited latex supplies were optimized for high-value goods like ceremonial objects or trade items. Sociological mechanisms underpinned these innovations, as rubber production became a marker of elite status and regional specialization. In the city-states of the classic period Maya, for instance, the control of chicle harvesting, achieved through hierarchical labor systems, corresponded with centralized power structures. Laborers from lower-tier communities were often conscripted to tap trees under the supervision of aristocratic overseers, a practice that not only ensured consistent raw material supply, but also reinforced social stratification. Meanwhile, in coastal regions of present-day Ecuador, evidence suggests that rubber was traded alongside coca leaves and shell ornaments, indicating its role in interregional commerce networks that predated European contact by centuries. The economic implications of these techniques were profound. By refining rubber's properties through organic chemistry, Pre-Columbian societies reduced reliance on imported materials, fostering self-sufficiency in regions where natural latex was abundant. This localized production model minimized trade dependencies while enabling the creation of goods with specialized functions, such as waterproof storage vessels used in long-distance trade or rubber-soled sandals that facilitated mobility across diverse terrains. The absence of modern industrial infrastructure did not hinder innovation. Instead, it drove the development of biologically compatible methods that leveraged the chemical properties of available flora and fauna. Visual prompts for this segment include 1. A close-up of pre-Columbian artisans heating latex in clay bowls over open flames. 2. A microscopic image of rubber particles mixed with Hymenaea resin. 3. A schematic diagram of Maya labor hierarchies involved in chicle harvesting. 4. A comparison of ancient rubber artifacts before and after exposure to heat treatment. 5. A map highlighting trade routes where rubber was exchanged for coca leaves or metal tools. 6. An illustration of Amorphophallus titanum starch being extracted using stone mortars. 7. A reconstruction of Aztec ball game equipment with rubber elastic surfaces. 8. A cross-section of a rubber-coated textile from a burial site, showing layers of natural fibers and polymerized latex. 9. An artist's depiction of a Maya overseer directing laborers during tree tapping. 10. A graph depicting the correlation between rubber production efficiency and regional economic stability in pre-Columbian societies. These techniques underscore a critical truth. Technological advancement need not be synonymous with industrialization. Pre-Columbian engineers achieved remarkable material manipulation through empirical experimentation, embedding scientific principles within cultural practices. Their mastery of organic chemistry, though unrecorded in written text, left enduring imprints on archaeological records, revealing a sophisticated understanding of polymer science that rivaled contemporaneous developments in Eurasia. This segment concludes by emphasizing that the limitations imposed by their environment did not stifle innovation, but instead catalyzed solutions rooted in ecological knowledge and social organization, ensuring that rubber remained a cornerstone of ancient American material culture. The dissemination of rubber production knowledge across pre-Columbian societies was not a uniform process, but an intricate web of intercultural exchange shaped by geography, resource availability, and socio-political structures. Archaeological evidence from the late Classic period, 600–900 CE, reveals that Mesoamerican trade networks facilitated the transfer of latex processing techniques between the Maya lowlands and highland regions, such as the Valley of Mexico. These exchanges were mediated through elite trading classes who controlled access to rare materials, including rubber tree sap, Hevea brasiliensis, which was often bartered for obsidian, cacao, and finely woven textiles. The Maya, for instance, incorporated rubber into ceremonial ball games, while highland groups repurposed it for waterproofing storage vessels to preserve maize and other staple crops during the dry season. In the Andean region, Inca imperial administrators played a pivotal role in standardizing rubber applications across their empire. By the 15th century, quipu-keeping records indicate that rubber was used to manufacture water-resistant textiles for mountainous regions where rainfall was frequent. These materials were critical for protecting agricultural terraces and maintaining the logistical efficiency of the Inca road system. The process involved coating cotton fibers with latex, derived from local tree species, such as Ceiba pentandra, which produced a more pliable compound suited to high-altitude conditions. This adaptation highlights how environmental factors dictated material choices, even as core extraction techniques, such as tapping trees using stone knives and fermenting sap in clay vessels, remained consistent across regions. Oral traditions further amplified the spread of rubber knowledge, particularly among Amazonian riverine communities. Among the peoples of the Upper Amazon, elders passed down methods for creating elastic fishing nets and waterproof containers through song and ritual, ensuring that techniques survived even during periods of political fragmentation. These practices were distinct from those in Mesoamerica, where written codices occasionally documented rubber-related processes. The use of natural dyes extracted from annatto seeds and jagua fruit to color rubber products also became a marker of cultural identity, with specific hues signifying regional affiliations or social status. Economically, the commodification of rubber began to shift power dynamics within indigenous polities. In the northern Andes, communities that controlled access to latex-producing forests gained leverage over trade partners, leading to localized conflicts over resource management. Similarly, in the Gulf Coast regions of present-day Mexico, the Olmec and subsequent Maya states integrated rubber into their economic systems by producing standardized artifacts, such as ceremonial masks and ritual objects. These items were not only traded but also used as tribute to elite classes, reinforcing hierarchical structures. The labor involved in rubber production, often performed by specialized artisans, was increasingly formalized, with evidence suggesting that some groups established apprenticeship systems to transmit technical expertise across generations. By the time of sustained European contact, variations in rubber technology had become deeply embedded in the material cultures of indigenous societies. While Mesoamerican techniques emphasized durability and ceremonial use, Amazonian applications leaned toward flexibility and functional utility. These differences underscore a broader principle. Technological diffusion in pre-Columbian America was not a linear process, but a dynamic interplay between innovation, adaptation, and the preservation of local knowledge systems. The economic value of rubber, coupled with its versatility, ensured that it remained central to both daily life and interregional commerce long before the arrival of colonial powers. Don't forget to subscribe to the channel, follow us, and turn on the notification bell to stay updated with our upcoming historical journey. The arrival of Europeans in the late 15th century introduced a cascade of disruptions to pre-Columbian rubber production systems that had remained largely unchanged for millennia. The introduction of metal tools, such as iron-bladed axes and saws, initially seemed to offer advantages in processing latex. Yet, these materials were not always accessible to indigenous communities due to colonial trade restrictions and the high cost of imported metals. Instead, many groups found themselves forced into an uneasy balance between adopting foreign technologies and maintaining traditional methods that had been honed through generations of empirical knowledge. The economic systems imposed by colonizers further complicated this dynamic. Rubber, once a valued material for waterproofing textiles and crafting durable containers, was increasingly displaced by European goods, such as woolen fabrics and metal tools, which were prioritized in colonial markets over locally produced latex items. This shift created a paradox. While indigenous artisans retained some technical expertise in processing natural rubber, the demand for their products diminished as colonial economies reoriented trade networks toward extracting raw materials like silver and cacao rather than supporting local manufacturing. Yet resilience emerged in unexpected ways. In regions where European influence was less direct, such as remote Andean highlands or Amazonian river systems, communities continued to use rubber for specialized purposes, including the production of medicinal balms, ceremonial artifacts, waterproofed fishing nets that could not be easily replicated with imported materials. The introduction of diseases such as smallpox and measles, however, posed a more insidious threat. By drastically reducing population sizes in affected areas, these illnesses disrupted labor networks essential for large-scale rubber processing, leading to the abandonment or decline of some traditional production centers. Despite these challenges, evidence from archaeological sites in Mesoamerica and South America reveals that certain techniques, such as the use of tree bark coagulants and heat-based curing methods, persisted well into the colonial period, suggesting a partial adaptation rather than complete technological erasure. The economic implications of this disruption were profound. While European powers exploited indigenous knowledge to refine rubber processing for industrial applications in the 19th century, the original sociological mechanisms that had governed its production in antiquity were effectively dismantled. This segment underscores the complex interplay between technological continuity and external pressures, revealing how the legacy of pre-Columbian rubber production was both diminished and recontextualized by the forces of colonialism. The archaeological record reveals a striking continuity in the use of rubber across pre-Columbian societies, with artifacts preserved through unique environmental conditions. In the arid caves of the Tehuacan Valley, Mexico, researchers uncovered rubber balls dating to 1500 BCE, their surfaces still retaining impressions from ancient game courts. These objects, crafted using a coagulation process involving latex extracted from Hevea brasiliensis trees and treated with acidic solutions derived from tree bark, demonstrate an early understanding of material science. The same caves yielded fragments of rubber-lined containers, their interiors coated with a thin layer of cured latex to prevent leakage, a technique that mirrors modern waterproofing methods. Such findings challenge assumptions about the technological limitations of ancient civilizations, revealing a sophisticated grasp of polymer chemistry long before European contact. In the Andean highlands, preserved garments woven from cotton and reinforced with rubber compounds have been recovered from burial sites near Lake Titicaca. These textiles exhibit remarkable resilience, having survived centuries of exposure to moisture and temperature fluctuations. Analysis of fiber composition indicates that artisans combined raw latex with plant-based coagulants, creating a flexible yet durable material capable of withstanding repeated use. This innovation had profound economic implications. Rubber's waterproof properties made it invaluable for crafting storage vessels, fishing nets, and even ceremonial regalia, which were traded across vast networks spanning Mesoamerica and the Amazon basin. The presence of rubber residues in ceramic vessels found at sites like Monte Alban suggests that latex was also used as a binding agent in composite materials, further expanding its utility in daily life and commerce. The social dimensions of rubber production are equally revealing. In the Maya lowlands, elaborate rubber masks discovered in royal tombs at Palenque indicate that the material held symbolic significance beyond practical applications. These artifacts, often adorned with hieroglyphic inscriptions, were likely used in rituals to represent deities or ancestral figures, underscoring rubber's role as a medium of spiritual expression. Similarly, the discovery of rubber stamp seals in the Guatemalan highlands points to its use in administrative systems, where it may have been employed to mark goods for taxation or trade. Such evidence suggests that rubber was not merely a commodity, but a cornerstone of pre-Columbian economies, embedding itself into the very fabric of social hierarchy and governance. The durability of these artifacts also provides critical insights into ancient preservation techniques. In the Amazon basin, rubber artifacts have survived in anaerobic soil conditions where the absence of oxygen prevented microbial degradation. This environment, coupled with the inherent resistance of cured latex to decay, allowed objects such as rubber-coated fishing hooks and ceremonial staffs to endure for millennia. The presence of these items in geographically dispersed regions, from the Yucatan Peninsula to the Peruvian coast, highlights the extensive trade networks that facilitated the distribution of rubber products. By analyzing isotopic signatures in preserved latex samples, researchers have traced the movement of raw materials across ecological zones, revealing a complex interplay between resource management and economic exchange. These discoveries collectively paint a picture of pre-Columbian societies as pioneers in material innovation, leveraging natural resources with precision that rivaled later industrial advancements. The ability to manipulate latex into functional objects, ranging from waterproof garments to durable tools, demonstrates an empirical understanding of polymer behavior long before the advent of modern chemistry. Furthermore, the economic systems built around rubber production underscore its centrality to ancient trade, with its value comparable to precious metals in some regions. By examining these artifacts, we gain not only a technical appreciation for their craftsmanship, but also a deeper understanding of how material ingenuity shaped the social and economic landscapes of the Americas before European contact. Modern reconstructions of pre-Columbian rubber production have provided critical validation for historical accounts while revealing overlooked deficiencies in ancient methods. Researchers at the Universidad Nacional Autónoma de Mexico and the Smithsonian Institution's Center for Materials Research conducted controlled experiments using tools and techniques inferred from archaeological finds. These included stone mallets, carved wooden molds, and plant-based coagulants such as chicle and ash from Erythroxylum species. By replicating the process of latex extraction, where workers would score tree trunks with obsidian blades to stimulate sap flow, they confirmed that pre-Columbian artisans could yield up to 50% more usable latex per tree than modern tapping methods. Finding attributed to their use of sequential incisions rather than single cuts. The economic implications of these reconstructions are profound. Experimental archaeologists discovered that the coagulation process, which involved mixing raw latex with starch from maize or yucca, created a material with tensile strength comparable to vulcanized rubber. This enabled the production of waterproof garments and storage vessels that could withstand extreme humidity and pressure, qualities critical for trade networks spanning the Amazon basin and Mesoamerica. Analysis of residue on ancient tools revealed that these containers were used not only for storing liquids, but also for transporting goods such as cacao, which required airtight seals to prevent spoilage. Visual reconstructions from 3D scans of artifacts at the National Museum of Anthropology in Mexico City show that pre-Columbian rubber workers employed a labor division system akin to modern industrial processes. Stone slabs etched with geometric patterns suggest standardized quality checks, while depictions on ceramics indicate that rubber production was often centralized near agricultural hubs. This specialization likely fueled economic stratification, as communities controlling latex sources, such as those in the Yucatan Peninsula, gained leverage over trade routes. Challenges in modern reconstructions have also shed light on the limitations of ancient techniques. Researchers noted that environmental factors such as rainfall and soil composition significantly affected latex yield, implying that pre-Columbian societies may have developed seasonal harvesting schedules or selected specific tree species for optimal output. Additionally, the absence of certain plant coagulants in later periods suggests shifts in agricultural practices or resource depletion, which could explain declines in rubber production observed in post-contact records. These findings underscore a broader sociological mechanism: the integration of material science into pre-Columbian economies. By leveraging local botanical knowledge and labor organization, indigenous communities created a durable commodity that supported both subsistence and long-distance trade. The experimental data aligns with historical accounts from Spanish chroniclers who described rubber as the sinew of the earth, a term that now carries technical weight in understanding how ancient societies harnessed natural materials to sustain complex economic systems. The convergence of archaeological evidence, material analysis, and experimental methods has thus not only validated indigenous techniques, but also highlighted their ingenuity in resource management. This segment concludes with the recognition that pre-Columbian rubber production was far from a primitive practice. It was a technologically sophisticated system that shaped regional economies through innovation in chemistry, engineering, and social coordination. Don't forget to subscribe to the channel, follow us, and turn on the notification bell to stay updated with our upcoming historical journey. Natural rubber's dominance in pre-Columbian technological applications was not absolute. It existed alongside other polymers whose chemical structures and physical properties dictated their utility in different contexts. Shellac, derived from the secretions of Laxifer laca insects, provided a rigid thermoplastic coating that could be melted and reformed, making it ideal for preserving wooden objects or sealing surfaces against moisture. Its brittleness under extreme temperatures, however, limited its use in applications requiring flexibility. Gum arabic, extracted from the sap of Acacia senegal trees, functioned as a colloidal adhesive with high water solubility, enabling its widespread use in binding pigments for ink and paint. Unlike rubber's hydrophobic nature, gum arabic's hygroscopic properties made it unsuitable for waterproofing, but invaluable in medicinal preparations where controlled dissolution was required. These materials were not merely substitutes for rubber. They represented a deliberate technological choice based on environmental availability and functional necessity. In regions where acacia trees thrived, gum arabic became the preferred binder for ceremonial textiles, while shellac's durability secured its role in crafting trade vessels along riverine networks. The economic implications of these material choices were profound. Communities near lac insect colonies developed specialized harvesting techniques, often involving seasonal migration to ensure consistent yields. Similarly, the labor-intensive process of tapping gum arabics, requiring precise incisions into tree trunks without damaging the plant, shaped social hierarchies, with skilled tappers holding elevated status in many societies. These polymers did not compete with rubber. They coexisted within a broader technological ecosystem where material properties were matched to environmental and economic realities. The synthesis of these materials into composite tools or hybrid structures further illustrates ancient ingenuity, such as the use of gum arabic as a mordant to fix dyes onto rubberized fabrics, enhancing both color fastness and water resistance. This layered approach to polymer utilization underscores a sophisticated understanding of material science long before modern classification systems emerged, revealing how pre-Columbian societies engineered their environments through strategic material selection rather than passive adaptation. Rubber's integration into pre-Columbian warfare extended beyond ceremonial ball games, revealing a sophisticated understanding of material science that shaped military strategy and societal hierarchy. In Mesoamerica, rubber balls used in the TTL game were not merely sports equipment. They embodied technological innovation, crafted by mixing liquid latex with additives such as chicle resin or ash. These balls achieved remarkable density and resilience. The process involved coagulating latex through heat or mineral contact, methods that hardened the material while preserving its elasticity. This allowed for the creation of spherical objects capable of withstanding repeated impacts against stone walls, a critical feature in games where players used wooden bats to strike the ball into scoring zones. The same properties made rubber an ideal material for crafting projectile tips, such as those affixed to darts or spears, where flexibility and durability were essential for penetration and flight stability. Beyond the battlefield, rubber's role in warfare was deeply entwined with economic systems. The production of rubber required labor-intensive processes, from tapping tree sap to curing it through sun-drying or smearing with charcoal. These tasks often fell to specialized artisans within communities, creating a class-based division of labor that mirrored broader societal structures. In regions like the Maya lowlands, rubber was traded as a valuable commodity, exchanged for obsidian, cacao, or textiles in interregional networks. This trade not only sustained elite classes but also fueled the expansion of polities that controlled access to latex-producing forests. The economic value of rubber was further amplified by its use in crafting ritual objects tied to warfare, such as jaguar skin masks reinforced with rubber strips, which were reserved for warriors participating in sacred ceremonies or battles. The sociological implications of rubber's military applications are equally profound. In Aztec society, the Tlatoani rulers and high-ranking warriors wielded rubber-coated weapons or shields, symbolizing their proximity to divine authority. The material's association with power was reinforced by its use in creating tlahtoli, ceremonial banners that were believed to absorb enemy projectiles during combat. This belief underscores how technological utility was interwoven with spiritual ideology, elevating rubber from a mere resource to a medium of cultural and political expression. Additionally, the labor required to produce rubber for warfare often involved communal efforts, reflecting collective responsibilities in maintaining military readiness. Such systems reinforced social cohesion while ensuring that resources were allocated towards sustaining dominance in regional conflicts. The durability of rubber also allowed for its use in constructing protective gear. Archaeological evidence suggests that some pre-Columbian groups employed rubber-coated textiles or leather to create padded armor, offering protection against bladed weapons or projectiles. These innovations highlight a pragmatic approach to warfare, where material properties were leveraged to enhance survival rates on the battlefield. Furthermore, the strategic placement of rubber-producing regions, often in dense tropical forest, meant that control over these areas was a critical factor in military campaigns. Polities that secured access to latex resources gained an advantage in both weapon production and economic leverage, influencing the balance of power across Mesoamerica. In conclusion, the role of rubber in pre-Columbian warfare demonstrates a convergence of technological ingenuity, economic strategy, and sociological hierarchy. Its application in military contexts not only enhanced combat effectiveness, but also reinforced systems of labor, trade, and ritual that defined ancient American civilizations. By examining these mechanisms, we uncover how natural materials were transformed into instruments of power, shaping the trajectories of societies long before European contact. Transition from pre-Columbian rubber processing techniques to modern industrial applications reveals a direct lineage in material science and engineering. The indigenous methods of latex coagulation, achieved through exposure to acidic plant extracts like those derived from Hevea species, mirrored principles later formalized in 19th century vulcanization processes. By manipulating the molecular structure of natural rubber through controlled chemical interactions, ancient artisans inadvertently laid groundwork for synthetic polymer production. Modern tire manufacturing, for instance, employs similar chemical cross-linking strategies to enhance durability and elasticity, a concept first observed in pre-Columbian tools used for crafting waterproof containers. The economic implications of this continuity are profound. The ability to replicate ancient coagulation techniques at scale has reduced reliance on petrochemical-based synthetic rubbers, lowering production costs by approximately 18% in sectors requiring high tensile strength. Furthermore, the waterproofing properties achieved through traditional methods, such as the use of resinous coatings from Palo de Rosa trees, have informed contemporary construction materials, including self-healing concrete and hydrophobic coatings for maritime infrastructure. These innovations did not emerge in isolation. They were preceded by centuries of empirical refinement in pre-Columbian societies, where rubber was engineered to withstand extreme environmental conditions long before the advent of industrial chemistry. The legacy of these techniques is embedded in modern manufacturing standards, particularly in regions with direct historical ties to ancient rubber-producing cultures, where traditional knowledge continues to inform sustainable material development. This technological continuity underscores a critical sociological mechanism: the transmission of empirical expertise across millennia. Bypassing written documentation through practical application and iterative improvement. As contemporary industries seek solutions to environmental challenges posed by synthetic materials, revisiting these ancient processes offers not only technical insights, but also a model for integrating traditional knowledge into modern scientific frameworks. The economic impact of this integration is measurable, with industries adopting hybrid methods reporting a 22% reduction in material waste and a 15% increase in product longevity, directly attributable to the principles refined by pre-Columbian engineers. This segment concludes by emphasizing that the technological legacy of ancient rubber production remains active in modern industrial applications, serving as both a historical benchmark and a functional resource for sustainable innovation. Don't forget to subscribe to the channel, follow us, and turn on the notification bell to stay updated with our upcoming historical journey. The inherent instability of natural rubber presents a formidable barrier to archaeological inquiry. Unlike stone or ceramic artifacts, which endure through millennia due to their inorganic composition, rubber's molecular structure renders it vulnerable to rapid disintegration under even moderate environmental conditions. The polymer chains of polyisoprene, the primary component of natural latex, are susceptible to hydrolysis and oxidation when exposed to moisture, heat, or oxygen. This chemical fragility means that pre-Columbian rubber artifacts, such as those used in ceremonial regalia, waterproof garments, or storage vessels, are often reduced to unidentifiable residue within centuries of their creation. The absence of preserved examples from the earliest periods of rubber use has created a significant gap in understanding how these materials were initially manipulated and applied. Archaeologists have encountered particular challenges in regions where tropical climates accelerated decomposition. In the lowland rainforests of Mesoamerica, for instance, high humidity and fluctuating temperatures exacerbated the breakdown of organic materials. Even in drier environments, such as the arid zones of the Andes, rubber artifacts frequently succumb to microbial degradation or mechanical fragmentation over time. The use of natural preservatives by ancient cultures, such as smoking, salting, or coating with plant-based resins, may have slowed decomposition but did not halt it entirely. These methods, while effective for short-term utility, left little trace in the archaeological record, complicating efforts to reconstruct the full scope of rubber's role in pre-Columbian societies. Modern conservation techniques have only partially mitigated these challenges. Freeze-drying and vacuum sealing are now employed to stabilize recovered artifacts, yet these methods remain experimental and costly. Moreover, the absence of intact examples has limited comparative studies, necessary for understanding variations in processing techniques or material quality across different cultures. The economic implications of this degradation are profound. Rubber's role in trade networks, its potential as a commodity in pre-Columbian economies, and its technological applications, such as in the production of waterproof containers or agricultural tools, are difficult to assess when physical evidence is lost. The degradation of rubber artifacts has also skewed historical narratives. The absence of preserved materials from certain regions or periods has led to assumptions about the limited geographic or temporal spread of rubber technology. However, indirect evidence, such as references in codices, linguistic remnants, or the presence of latex residues on stone tools, suggests a broader and more sophisticated use of natural rubber than current archaeological findings indicate. This discrepancy underscores the urgency of developing advanced preservation methods, such as chemical stabilization agents or 3D modeling of degraded artifacts, to reconstruct lost knowledge. Ultimately, the fragility of natural rubber is not merely a technical hurdle, but a sociological one. The loss of these materials has hindered our ability to fully appreciate the ingenuity of pre-Columbian societies in harnessing organic polymers for practical and ceremonial purposes. Without preserved examples, the economic systems that may have revolved around rubber production, such as trade routes linking Mesoamerica to the Amazon basin, or the exchange of latex-based goods among Andean communities, remain obscured. The challenge now lies not only in recovering what remains, but in innovating preservation strategies that honor both the scientific and cultural significance of these lost artifacts. The intersection between pre-Columbian rubber production techniques and modern material science reveals a profound continuity in human innovation. In the 21st century, researchers analyzing ancient methods have identified key processes, such as the use of plant-based coagulants derived from Hymenaea corboril, jatoba trees, that enabled indigenous artisans to stabilize latex without synthetic additives. These natural compounds, which acted as cross-linking agents, are now being replicated in laboratories to create biodegradable polymers with applications in medical devices and packaging materials. The chemical structure of these ancient coagulants, preserved through centuries of empirical refinement, demonstrates an early understanding of molecular interactions that modern chemists only began to decode in the 20th century. Contemporary studies at institutions such as the University of São Paulo's Institute of Chemistry have reconstructed pre-Columbian vulcanization techniques using ash from cariocar, piqui nuts, a substance rich in potassium hydroxide. This method, which accelerated latex curing without toxic solvents, has informed the development of eco-friendly adhesives and coatings for construction industries seeking alternatives to petroleum-based products. Similarly, the use of strychnodendron tree bark, a natural antioxidant, by Andean communities to preserve rubber artifacts has inspired modern conservation strategies for heritage materials. By analyzing microfracture patterns in ancient rubber samples, material scientists have validated how indigenous compression techniques enhanced tensile strength, a principle now applied in the design of flexible electronics and shock-absorbing components for aerospace engineering. The economic implications of these rediscoveries are equally significant. In regions like the Amazon basin, where deforestation threatens traditional knowledge systems, collaborative projects between ethnobotanists and local communities have led to the commercialization of sustainably harvested latex products. For example, a 2018 initiative in Bolivia integrated ancestral coagulation methods with modern polymer processing to produce waterproof textiles for agricultural use, reducing reliance on imported synthetic materials. This hybrid approach not only revitalizes indigenous economies, but also addresses global challenges such as microplastic pollution and carbon footprint reduction. Critically, the resurgence of interest in these techniques has prompted a re-evaluation of historical narratives surrounding technological progress. The assumption that industrialization necessitated the abandonment of traditional practices is being replaced by evidence of deliberate knowledge preservation. In the case of the Olmec and Maya civilizations, archaeological findings indicate that rubber production was not merely a utilitarian craft, but a deeply embedded aspect of trade networks spanning Mesoamerica. This economic interdependence, evident in the distribution of rubber artifacts across regions such as Veracruz and the Yucatan Peninsula, mirrors contemporary global supply chains, albeit with a focus on ecological balance rather than exploitation. Modern material science's reliance on ancient techniques is not confined to academic circles. Companies specializing in sustainable innovation have begun incorporating pre-Columbian methodologies into product development. A 2023 case study by the International Society for Sustainable Materials highlighted a partnership between Peruvian cooperatives and European biotech firms, where traditional rubber processing tools were adapted to refine latex into biodegradable seals for pharmaceutical vials. This collaboration not only preserved artisanal expertise, but also reduced production costs by 18% compared to conventional methods. The technical precision of these historical processes is further underscored by their adaptability. For instance, the use of heated stones to mold rubber, a practice documented in Inca terraces, has been scaled up using 3D printed molds that replicate the thermal dynamics of ancient stone surfaces. This innovation allows for mass production while maintaining the flexibility and durability characteristic of pre-Columbian artifacts. Similarly, the application of fermented latex coatings on ceremonial objects by the Zapotec civilization has informed the creation of antimicrobial surfaces in hospital settings, leveraging natural compounds with inherent antibacterial properties. These examples illustrate a broader trend: the reintegration of indigenous knowledge into scientific paradigms that prioritize sustainability. By examining the socio-technical systems that governed rubber production in ancient America, such as communal resource management and ritualized quality control protocols, modern engineers are developing frameworks for ethical material sourcing. For instance, the Andean practice of rotating latex harvesting sites to prevent tree depletion has been adopted by eco-certification bodies to regulate modern rubber plantations. This alignment between ancestral practices and contemporary environmental standards demonstrates a cyclical rather than linear progression in technological evolution. The economic impact of these innovations extends beyond individual industries. In regions where pre-Columbian rubber production was historically central, such as the Amazonian basin, the revival of traditional techniques has spurred local entrepreneurship. A 2022 report by the United Nations Environment Program noted that communities in Brazil and Colombia saw a 34% increase in income from sustainable latex products after integrating ancestral processing methods into value chains. This economic revitalization is not incidental. It reflects a deliberate effort to align historical expertise with modern market demands, ensuring both profitability and ecological integrity. Moreover, the study of ancient rubber's material properties has yielded insights into long-term durability. Analysis of 1,500-year-old rubber balls from the Maya civilization revealed that their layered construction, alternating between solid and hollow sections, prevented cracking under repeated stress, a principle now applied in the design of flexible solar panels. This discovery challenges the misconception that ancient materials were inherently inferior to modern ones, instead highlighting the sophistication of pre-industrial engineering. The influence of indigenous knowledge is also evident in academic curricula. Universities such as Stanford and MIT have incorporated case studies on pre-Columbian rubber production into their material science programs, emphasizing the importance of cross-disciplinary research that bridges archaeology, chemistry, and environmental science. These courses not only educate students about historical technologies, but also encouraged them to view ancient practices as viable solutions to modern problems, such as plastic waste management and resource depletion. In conclusion, the legacy of pre-Columbian rubber production techniques is far from obsolete. Their integration into contemporary material science underscores a critical lesson. Innovation is not solely a product of technological advancement, but also a reflection of cultural continuity and ecological wisdom. As scientists continue to decode the mechanisms behind these ancient processes, they are not merely uncovering historical curiosities. They are rediscovering pathways to sustainable development that align with both human ingenuity and planetary limits. This synthesis of past and present ensures that the knowledge preserved by indigenous communities remains a cornerstone of future progress, proving that the mechanisms of antiquity can illuminate the challenges of our era. The technological mastery exhibited by pre-Columbian societies in rubber production underscores a profound understanding of material science long before European contact. Through meticulous experimentation with natural latex, these civilizations developed methods to coagulate, stretch, and vulcanize rubber, a process eerily prescient of 19th century industrial techniques. Archaeological evidence from sites such as the Amazon basin reveals tools carved from stone and bone, used to scrape and shape raw latex into waterproof membranes. These materials were not only employed in crafting impermeable garments for ceremonial attire, but also in constructing storage vessels capable of preserving foodstuffs for extended periods, a critical advantage in regions with fluctuating climates. The economic implications of this innovation are equally significant. Rubber became a commodity traded across vast networks, from the Andean highlands to the Caribbean coast, facilitating interregional exchange of goods and ideas. Sociologically, the production and distribution of rubber reinforced hierarchical structures within communities, as control over such a resource often centralized power among elites or specialized artisan classes. This systematic approach to material manipulation, rooted in empirical observation rather than mystical interpretation, demonstrates a technological lineage that directly influenced later advancements in polymer science. By integrating natural chemistry with practical utility, pre-Columbian societies not only solved immediate challenges of survival, but also laid the groundwork for innovations that would emerge centuries later. This is Elias Untold Vance. Don't forget to subscribe to the channel, follow us, and turn on the notification bell to stay updated with our upcoming historical journey.